We've all heard of quantum computers. They're the future. It's sci-fi in real life. They're amazing and magical, and they can calculate every possibility at the same time. Now, while quantum computers are pretty cool and they definitely are the future, a lot of this is misleading, and we're going to clear some of that up in this video. A key difference between quantum computers and what we call classical computers is the amount of times that you run a program. A quantum program is not just ran once. If you ran a quantum program once, you'd basically get noise. You wouldn't even be guaranteed to have a correct answer. And this is due to a key difference fundamentally between quantum computers and classical computers. Because in quantum computing, we're not running on definite values. We're running these quantum programs to get a probability distribution of what the answers will be. And we do our calculations based on this probability distribution. Quantum computers are less like call a function and get a value, and they're more like run an experiment many times and estimate something. Classical programs compute outputs, while quantum programs often produce statistics. Let's get more into the details. Before we get too deep into the details about what quantum programs actually are and how you go about writing a quantum algorithm, we need to define and understand what they actually are. So a quantum program is usually a circuit or a quantum kernel, and you use it to prepare qubits, apply gates to those qubits, and then take some measurement. Most quantum code is not a full standalone application, but it's usually a specialized computational subroutine inside a larger classical workflow. Now, a lot of current quantum SDKs are built around either sampling measurement outcomes or estimating observables. So the return value of a quantum program often isn't a normal scalar value like true or false or some data. You're typically going to get counts, probabilities, or an estimated expectation of value. And this is due to the key difference between quantum computers and classical computers, where in quantum computing, we're working with a probability distribution and not definite values. Quantum computers are highly sensitive machines that run on very specialized environments. And because of this, a lot of times real life quantum computers either live in government facilities or inside some large corporation that can afford to create these specialized environments. Your source circuit is not what runs on the hardware literally. When you run a quantum program, it's not going to be running locally on your computer like you might do with a node server or some Go program. It's going to be reaching out to these companies via SDK and running on their physical hardware. Now, some steps to create this circuit would be you have to write it, it gets compiled, and then it gets mapped to physical qubits on the device. Some extra routing gates may be inserted because hardware connectivity is limited. Now, a key thing to remember is real quantum chips don't have all-to-all connectivity, so where your qubits live, physically it matters. To execute these quantum circuits, well, it runs, you take that measurement, and that destroys the quantum state, so the next shot starts from a fresh initialization. And this is a key thing to remember about quantum computers is that when you have your qubits in a quantum state, you take that measurement and that quantum state collapses into a more classical result. So to run it again, you just set everything up, put the qubits back in their quantum state, take another measure it, collapse the state, and continue. Now, a comparison we can make here is a classical program can keep updating memory step by step, whereas a quantum computer or quantum program usually ends when you measure the state. A difference in the simulation versus hardware is on a simulator, you can sometimes inspect the full state vector, but on real hardware, you usually only get measurements and derived statistics. On a real quantum computer, you don't get to peek inside the state whenever you want. Probably the biggest mindset shift for developers when comparing quantum programs to classical programs is the idea that you need to run a quantum program many times over to get any useful information. This is in direct contrast to a regular computer program like a JavaScript function or a Go function, where you write a function, you have some input, and then you'll get an output. And assuming the function is pure or deterministic, given the same input, you'll get the same output. With a quantum program, you need to run it many times over, or else you're just kind of wasting your time. If you ran a quantum program once, you'd get one bit string and one measurement outcome, and you'd be missing the full picture. Many shots gives you a histogram or a distribution of results, an estimated probability, an expectation of value, and it'll give you some kind of confidence about what the result is. Let's use an example of a bell pair, which is really just a pair of qubits that is entangled. If you measure it once, you might get 0, 0 or 1, 1, but that doesn't really prove anything. You're missing a lot of context and a lot of information. But if you run the program 1,000 times and get roughly half 00 and half 11, you'll see the full structure of the output and you can make a more accurate prediction on the results. Now, more runs means less sampling noise, and your estimate gets more stable as shots increase. A lot of quantum algorithms don't even want one sample. They want a probability pattern or expectation value computed from many steps. Repetition is not a workaround in quantum computing, it's part of the model. It's a fundamental piece of how quantum computing works and uses that probability distribution. I've been throwing around words like non-deterministic, probabilistic, and probability distribution, and this is where a lot of people get confused, so it helps to break it down into two layers. Layer 1, evolution is deterministic. The math of the quantum state evolving under whatever gates you apply to it is deterministic. If I apply a known gate sequence to an ideal state, the resulting state is mathematically determined. There's layer 2, where measurement is probabilistic. Once you measure, the outcome is generally a probability distribution. The program doesn't really return the state, it returns a sampled measurement outcome from that state. So as an example, let's use a Hadamard gate, which is really just a simple quantum gate that takes a qubit and puts it into superposition. If we start with qubit A, that's in a state 0, we apply a Hadamard gate to it. In an ideal theory, once you measure that qubit A, there's a 50% chance it's a 0 and a 50% chance it's a 1. Once you run that quantum program once, you would either get a 0 or 1. But when you run it many times over, that's when that 50-50 pattern is revealed and you get more of the bigger picture. Now, a thing to note is that in real life, these quantum computers are very sensitive and they're prone to let noise mess with the results. So you have the ideal quantum probability plus the physical hardware error on top of that. Quantum programs are not just random, the evolution is structured, but the readout is often probabilistic. Now that we know a little bit about what quantum programs are and how they work, we can get more into the details about how they're different from a regular program. One big difference is you can't really inspect data the normal way. In classical code, like a JavaScript program, for example, you can print values whenever you want. But in quantum code, measurement changes the state, so debugging and introspection are fundamentally different. And quantum data is not like normal variables. A qubit is not just a fancy bit variable that you can read and write to whenever you want. You can transform it, entangle it, or measure it, but you can't treat it like a normal mutable variable that you can inspect at every line. A key thing to note is measurement is destructive. Once you measure, you collapse the state. That means that measurement is not just logging, it's part of the computation itself. And this comes from a lot of the quantum weirdness you get with qubits and other quantum particles. Once you make an observation of it, it has a definite value. You collapse its wave function, and now it's a physical thing that you can measure. Hardware constraints also have a big impact on quantum programs. In classical computing, you don't really care what transistor your code executes on, but in quantum computing, hardware layout, native gates, error rates, and coherence times all greatly matter. Two devices may run the same circuit very differently after compilation. And in quantum programs, the results are often statistical objects. So instead of getting a value, you might get counts, bit string frequencies, expectation values, or error bars. So this means that post-processing of data is a bigger picture and a bigger part of the workflow when working with quantum programs. Now, most real-world workloads are hybrid. Classical code usually prepares parameters, builds circuits, send jobs, etc. But the quantum computer is often one part of a classical optimization or simulation loop. And the language model can differ too. One example is Q#. Functions are deterministic, classical logic, but operations are the parts of the circuit that act on qubits. That split is a good mental model, so the classical control and the quantum action are not the same thing. So quantum code isn't just Python with weird gates added on top. It has a different execution model. In quantum programming, we use things called circuits, and there are two types. There are static circuits and dynamic circuits. Traditional quantum circuits are static. You define the whole circuit first, and then you run it. However, dynamic circuits are more like runtime logic. Measure the middle, use the result immediately, and condition later operations on that result. This is the closest thing quantum hardware has to real-time branching during execution. A good example would be quantum teleportation. You do a mid-circuit measurement, then apply a correction depending on the measurement result. It makes quantum programs feel more like programs and less like fixed experiments. But realistically, It's still limited compared with normal CPU control flow, where we're not at the point where a quantum program behaves like a normal operative program with arbitrary loops and branching on hardware. Dynamic circuits are where quantum computing starts to feel less like static circuits and more like runtime computations. Great, quantum computers are cool and quantum programming is interesting, but who cares? Why are quantum programs actually useful today? Well, quantum programs are not a replacement for normal software. You're probably not going to be building a web server or a game engine with a QPU or walking around with a phone that has a quantum chip in your pocket. It's better to think of quantum programs as a specialized accelerator workload, more like a strange coprocessor than a general replacement for CPUs. Some of the areas where quantum programs are being used today for some really cool stuff are chemistry simulation, optimization research, and algorithm exploration. Think of things like the traveling salesman problem. Classical computers still do orchestration, batching, scheduling, etc., but quantum computers handle these really hard problems that classical computers can't really do, like RSA encryption. Quantum computers are very good at analyzing that and cracking it. So right now, a good mental model would be classical program in charge, but the quantum subroutine for a narrower task that the classical computer has a really hard time with. The future's probably not quantum instead of classical, it's quantum plus classical. The three biggest ideas to remember about quantum programming versus classical programming is a classical program usually gives one answer from one run, and a quantum program often gives one sample per run, so repetition matters. And the state evolution of a quantum program can be deterministic, but the measurement outcome is often probabilistic. The mindset you need to have is you built a circuit, the hardware that circuit's on matters, measurement of a qubit is destructive, results are statistical, and most of the real world workflows for quantum computing are hybrid. The weird thing about quantum programs isn't just that they use qubits, it's that the meaning of a run is totally different each time. In classical computing, one run is often the result. In quantum computing, one run is often just one data point and part of a larger picture. If you enjoyed the video, like always, please hit subscribe, like the video. It means a lot to me and it really helps me out. We have more videos coming, not only about quantum computing and quantum programming, but about privacy as well. So as always, protect yourself, protect your code.